Getting triggy with it all of a sudden. Rotation angles in standard position. Angles can be measured in degrees, where 360 degrees is one complete rotation. And here's what we're going to say. For us to be able to keep going around and around, don't write this down, just watch. We're going to put every angle now on a graph where one arm of the graph is the positive x-axis, and the other arm is like the arm of a clock that can rotate that way to make a bigger and bigger and bigger angle. We call it a rotation angle. Standard position is where you're using the positive x-axis as one arm. The positive x-axis is one arm. So a rotation angle is formed by rotating an initial arm or initial side through an angle, and traditionally, my physics kids have seen this, we use the variable theta for an angle. Why? Well, the same way if I use x and y, I'm probably talking about a graph because it's x and y. The same way if I use a, b, and c, which equation am I probably talking about if I'm using a and b and c? Which one has a, b, and c in it? Pythagoras, right? It's traditional. If you see a theta as a variable, which is a zero wearing a belt, if you see a theta, hey, odds are it came from an angle. So it's Brianna, math shorthand. Also, we just kind of run out of letters, okay? So if we rotate an angle through theta degrees, we call this the initial arm. We call this the terminal arm, because this is where the angle terminates. And this is the vertex. That wasn't a good Arnold. I'll do a better one another time. We call this the rotation angle. Positive is this way. Negative is that way. In fact, we say positive is counterclockwise is actually the positive direction in the universe. Had I been in charge, clocks would run this way because it makes much more sense for lots of other physics applications. Why do they run this way? Do you know? What were the very, very first clocks? Sundials. It turns out the shadow of the sun does move clockwise. But we shouldn't have used that. The universe itself seems to prefer counterclockwise in most of its applications. Hashtag nerd trivia. Okay, back here. So this allows me now, Logan, to draw a picture of an angle. First of all, every quadrant is how many degrees? 90 degrees. So if I wanted to draw 235 degrees, I would go like this. 90. 90 more. How far? 180. How much further till I get to 235? Do the math. Preferably in your head, but you can use a calculator if you need to. This little tiny angle here is 45 degrees. This whole thing here is 235 degrees, and it's in standard position. 55? You're right, Mr. Dueck. I did the math bad in my head after I'm making fun of you guys. Sorry, guys. And we say that's in standard position because we started measuring from the positive x-axis. And we'll almost always start measuring from the positive x-axis. This also now allows me to define a negative angle. A negative angle is going in this direction. So negative 247 degrees would be negative 90, negative 180. How much further? Well, if I went here, that's negative 270. That's too far. This little smidge angle here is whatever 247 take away 180 is. This little smidge angle here is, double check me now, am I right? Is it 67 degrees, I think? And that gives you negative 247 degrees. Okay. So on your test, definitely I'm going to give you some angles and I'm going to say sketch them. These are kind of fun. It's as close as we come in math to drawing. 290 degrees. Positive or negative? Okay, so I'm going to go counterclockwise, and here's how I tend to do these. I kind of go, how far? How far? Now, instead of going 90, 180, I actually use my 9 times table because 90 is 9 times 10. So I think to myself, 9, 18, 27, 36 is too far. So certainly 290 degrees is going to be in here somewhere. Yeah? How big is this angle? That's how you can show me you're in the right place. You can either put a 70 there, or you could have put a 20 degrees there, but that's how I know that you figured out exactly where we are. Now, this is bad scale. I guess you could argue, don't write this down, that I should be closer like that. I'm usually not too fussy on your scale. I want the quadrant right, though. So I'll put it there like that just to make you guys happy. Heck no, whoop. Let's come back, Mr. Dueck. I'll leave it there. Negative 135. What does negative mean, Oscar? Which way am I going to go? So, how far? How far have I gone with that drawing right there? What's each quarter worth? I got to be fussy. Negative 90? If I went to there, how far would that be? Negative what? Too far. So I already know that I'm in this quadrant. And then I usually do a little arithmetic just to kind of fill in some gaps. I think 45 degrees and 45 degrees. I think that works. Yeah, 90 plus 45 is 135. Sorry, negative 90 and negative 45 is negative 135. Is that okay, Ashley? Next one. Laura, how big an angle did they give me? That's big. Okay? Positive? Here's how I would do this. Put your pencils down. I use the 9 times table. I'm going to see when I get to 75, not 750, 75. 9, 18, 27, 36. What comes after 36?
45.
That's 450 degrees. What comes after 45?
54.
That's 540 degrees. What comes after 54?
62.
That's 630 degrees. Next. 720 degrees. How much past 720 degrees till I get to 750 degrees? So I can even go, and I can even tell you that little angle right there is 30 degrees. There is a picture. Am I doing the right way for you? I got to reverse this all for you guys. There is a picture of 750 degrees. And you can go up to infinity. But we're not going to. Or at a negative infinity. We're not going to. Next page. In previous work, in all the trig that you've done so far, Mackenzie, using SOHCAHTOA, and then last year you also did the sine law, sine of big A over little a equals sine of big B over little b, and you did the cosine law, c squared equals a squared plus b squared minus 2ab cos c. In all of those, you used degrees. And degrees are nice, Brendan, in that you can do the math in your head, and most of you, because you've grown up with them, you know some of the values. Look up. How many degrees? 90. How many degrees? 180. Ready? 360. In fact, we use those in terminology in sports. They suck everywhere else. They're great for math in your head, and that's valuable. Radians have a much, 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 much better mathematical application. So, in order to simplify some calculations in mathematics, we use something called radians, or RAD for short. What's a radian? There's an exploration here. I'm just going to give you, this is the definition of a radian. You take a circle. See it? You call the radius r. That's how long it is. Put an r there. If you go the same length along this arc that the radius is, which would be, I'm eyeballing it, about that. If that distance is also r, this is 1 radian. It's the angle whose arc length and radius are the same. And you don't realize it yet, Rachel, but that's hugely useful, it turns out. It's hugely useful. Okay? A radian is defined as a ratio. Because it's a ratio, that means it doesn't have any units, unlike degrees. But if you write RAD, that's considered acceptable because you're saying it's in radians. But if you write nothing, that's also, I'll clue in, you're talking about radians. It's the ratio that compares the length of an arc to the radius. Here's the definition. The measure of an angle in radians is the length of the arc forming the angle divided by the length of the radius, or short, arc length over radius. Darian, you're looking hugely useful. No, I was just using my pen. It's that equals that over that. I think there was a little dot appearing that you could follow with your eyes, as it was the idea. It does in the video. Okay? So, big deal. Well, first of all, that means that 1 radian is about this big. In fact, if I take my arm and I do an arc about the same length as my forearm, that's about a radian. All of you kind of have one built in. It's kind of like this. Too big? Yes. Too small? Yes. This distance from about here to here is about the same distance as the length of my arm. So the first thing that does, that gives us a common distance that's independent of anything else. What else does it do? Next page. Okay. Since an angle can be measured in degrees or in radians, it helps to be able to convert from one to the other. Now, I have learned that your calculators do have a built-in converter. I'm not sure of the older ones. Sorry. But it's actually really handy to be able to do the easier ones in your head, because your calculators will only give you yucky decimal answers, and almost all of these are fractions, and the fractions are much easier to deal with. So you ready? Read along with me, Taylor. It says this. 1 complete rotation in degrees is, I know this, 360 degrees. You okay with that? Then it says, part 2, the arc length for 1 complete rotation is, I'm going to tell you what it is. It's the circumference of a circle. What's the equation for the circumference of a circle? Give you a hint. It's got an r in it, but it doesn't have a squared. So it's not pi r squared, that's the area. It's the other one.
2 pi r?
2 pi r. Okay. So once around the circle in degrees is what? 360. Remember that. And then 1 arc length around a circle is 2 pi r. And here's where we get kind of clever. Carson, we defined a radian as the arc length, which in this case is 2 pi r, if we go all the way around, divided by the radius. How many r's on top? How many r's on the bottom? Here it is, boys and girls. 360 degrees is 2 pi radians. That there is 360 degrees. That there is 2 pi. Okay. So, look up. look up, if all of this is 2 pi, let's try that again because the color was supposed to change, then how big is half a circle? How big is 180 degrees? 1 pi. That's the conversion factor we're going to use. That's the conversion factor we're going to use. And by using that, you're going to have to memorize that, Grayson, but by memorizing that, trust me, I'm going to show you clever tricks where you can get almost any other fraction that you happen to need. So what we're going to say is 1/2 rotation in degrees is 180 degrees. You know what? 180 degrees is pi radians. Put a box around this, please. Pi, 180 degrees. It's a different way to think about angles, I realize. Oh, by the way, it's also handy because, Rachel, pi has a lot to do with circles, and the fact that we're bringing pi into our measurement means later on it's going to cancel out stuff and give us nicer numbers. Because you'll have pi's elsewhere, and you'll have a pi on top and a pi on the bottom. Yay, they cancel! And so you don't get a long, repeating, yucky. Well, if 180 degrees is pi radians, I think 1 degree is if pi is 180, 1 degree is sorry, am I doing this right? Pi over 180 or 180 over pi? Yeah, pi over 180. To go from degrees to radians, multiply by pi over 180 degrees. Those of you that are in physics, I want degrees to cancel, so I put it on the bottom. Over on the left, 1 radian is 180 degrees over pi. To go from radians to degrees, those of you that are in physics, I want radians to cancel, so where am I going to put the pi? To get it to cancel? On the bottom, and that means the 180 degrees goes on the top. This is going to sound, this is going to seem, this is going to feel confusing. Relax. It's always getting into the shallow end, but you'll get used to the water and you'll start to swim. Trust me, I've done this before. Little nerd note. In mathematics, that symbol right there means degrees. If you don't put that symbol, I'll assume you mean radians. In other words, if you write this, I will not assume you mean 45 degrees. I'll assume you mean 45 radians. Degrees, radians. Or you can write the word rad if you really want to. Okay? So, little note. So, what you really need to remember is this. What you really need to remember is that pi radians is 180 degrees. Because that's the conversion factor. You can memorize this, but physics kids, I've taught you how to just say, oh, what do I want to cancel? That goes on the bottom in the conversion fraction. The other one goes on the top. Sorry to those of you who didn't take physics. Turn the page. Example 2 says, convert from radians to degrees. Ah, but Pam, what does it say in brackets? Okay. Darian, did they give me degrees or radians initially? What do I want to end up with? So in my conversion factor, which is going to have a 180 degrees and a pi in it, where am I going to put the degrees to get it to cancel? On the top or on the bottom? So everybody do this. How do you multiply fractions? It's the easiest. Top times top. Put your calculator away, just hang on. Bottom times bottom. The first answer would be this. It's 270 pi over 180. That's what they mean when they say leave it as an exact value in terms of pi, except we're going to ask you, reduce the fraction part. What is 270 over 180 in lowest terms? Now you can either do it in your head, because I think you can divide everything by 90, or you can use the fraction button on your calculator. You can go, if you wish. What? Okay, so you can go, if you wish, 270, fraction button, 180, which is 3. The answer here, don't forget the pi, Julia. We would say this. We pronounce that 3 pi by 2. We don't even say the word divided by. We've dropped that. It's 3 pi by 2. 270 degrees is the same as 3 pi by 2 radians. 315 degrees. I'm going to multiply by, I want the degrees to cancel, so the pi is going to go on top. It's going to be 315 over 180 times pi, which in lowest terms is what? Is it 7 pi by 4? 7 pi by 4. Now, right now, you're saying, Dueck, I don't see the use for this. I did say degrees are easier to do the math in your head. I'm not going to argue that. But give me a couple more lessons, and I'll start to convince you why radians are nicer in many, many other ways. Convert from, oh, Pam, can you read me the instructions again here?
Give your answer.
No, example 3.
Oh, example 3. To the nearest tenth.
You read the whole thing, please.
Oh, convert the following from degrees to radians.
Same as we did before. Oh, except this time what?
To the nearest tenth.
What they're saying is this time don't leave it as something by pi. All I'm going to do is this. I still want the degrees to cancel. So the 180 is going to go on the bottom. The pi is going to go on the top. But this time I'm literally going to go 70 times pi divided by 180. Your pi button is Shift X, Shift scientific notation. As a decimal, 1.22, to the nearest tenth, 1.2 radians. Yo, look up. Shift EXP right there. And please use the pi button. Don't use 3.14. That's terribly inaccurate. Don't type 3.14. Use the pi button. (205 degrees). Can you try on your own, convert that to radians to the nearest tenth, so don't leave it as a multiple of pi? And I get 3.6 ish. Is that okay? Yeah. So on your test, I will definitely say convert from degrees to radians. Sometimes I'll say leave it as an exact value. Sometimes I'll say give it to me as a decimal. Oh, if I ask you to go from degrees to radians, I'm also going to ask you to go from radians to degrees. Matt, from radians to what? Example 4, from radians to what? Okay. This time, I want degrees to stick around. Physics kids, if I want degrees to stick around, Darian, where am I going to put the degrees if I don't want it to cancel? Yep. And I'm literally going to go pi times 180 divided by 4 divided by pi. Or if you're really clever, you might notice how many pi's on top. 1. How many pi's on the bottom? I think the pi's will cancel. But if you're not sure, you can go pi times 180 divided by, just covering it over, Mr. Dueck, doesn't help much, 4 divided by pi. Or if you want to, you can use your fraction button, Rachel. You can go pi, oh, wrong button. Okay, exit, exit, exit. Pi, fraction button, 4 times 180, fraction button, pi, 45. Here's the point. You know what pi by 4 radians is the same as? How many degrees? Look up. That's pi by 4 radians. That's about 45 degrees, yeah? Pi by 4 radians is about that big. Try B on your own, please. I want to go from radians. I want to end up in degrees. Try it on your own. I'll do it up here if you get stuck. See if you get what I got. Is that okay, Kyle? 420 degrees? No? Am I wrong? I think I'm right. It is. Okay. Why would that answer there be wrong?
Got the degrees.
Okay, that's radians as far as I'm concerned. Try A, try B, and number 5. Convert them from radians to degrees. And then I'll show you how you can get your graphing calculator to do most of this for you, but not all of it. I know this one. I think it's going to be very, very close to that. Double check me. Is it close to 90?
Yeah, it's 89.9.
Yeah. It's closer than that, isn't it?
It is 89.95 actually. So we're looking at
Yeah. Nice try. I thought I knew
Sorry,
this.
I got time to lost already.
In the old math, we used to, over half the course was trig, and so you just got really good at moving around the circle in radians. You just got comfy with it. This one, I don't know. 1.4 times 180 divided by pi. 80.2. Mr. Dueck? Yeah, Zach. We got these fancy calculators, and we're doing a lot of work by hand. Will they do some of this? They will handle everything except the exact value questions. What they won't handle is something like example 2, where I wanted to leave the pi in the answer. But yes, you do. So you ready? We're going to do example 5A on our using technology. So clear your screen, but be in this menu. And can you type 1.57? Then, do you remember when we did combinatorics, we were able to bring in the factorial and the NCR? And what button did we hit to start to bring those up? Option. So can you hit the option button right there? Except, I don't want list factors. I don't want matrices. I don't want complex. I don't think I want calculations. I don't think it's there. I don't want stat. You know what? Let's go arrow sideways. Oh, which one do I think that I might want? Angles. What do you think that little circle stands for? Degrees. That'll change it into degrees. So is this one, do we want it to go into degrees? Nope, hang on. I got to think about this here. Ah, got a problem. I know what the problem is. Before we do this, we need to put our calculators in the right mode. How do we do that? So, can all of you please go Shift and then hit the Setup button, which is right above Menu. I'm in Radians right now. All of you right now, go to degrees.
That's convenient.
If you're already in degrees, you're fine. Anybody not there?
In angles, right?
No, we're in setup. Right now, your screen should look just like this.
No, I meant.
I'm not there yet. I'm saying get to this screen here and make sure that it says angle deg. Are you on this screen?
Yes.
Okay. I think now it'll work. Let me see. If we go exit and we go option, arrow sideways, angle, and I go 1.57, change it to degrees? No, 1.57, change it from radians into degrees? There. I'll be honest, Ashley, I don't find this a big time saver. To me, I long since have memorized, oh, it's 180 and it's pi, and I can figure out whether the pi is on the top or on the bottom. Really, I figure out whether the degrees is on the top or on the bottom. Do I want to end up in degrees? Make sure it's on the top. Do I want to cancel degrees? Make sure it's on the bottom. But the technology can do it, Darian. The technology can do it. You awake? Good. So this is for the TI graphing calculator. Zach, if you wanted to figure out how this works on your personal calculator, it's this, but I'm going to go, we're using our own different technology. Okay? What you do have to know, and what you're going to have to get good at, is flipping from degrees to radians. So it says trig ratios, degree mode and radian mode on a calculator. Look up. Okay? Yeah, Pam, talking to you. Brandon, you with me? Yeah. This question here, how do I know what mode I want my calculator in? What tells me? I'm going to hit the cosine button, but what mode do I want my angle measure in? Degrees. What about for this question here? I'm going to have to, before I do the math, I'm going to have to change my calculator to radians. What about this one here? What about this one here? Oh, wait, 90, isn't that degrees? Only if they put the degree symbol there. So, you ready? Let's start doing some trig. Let's get triggy with it. Degrees, so go shift, setup, make sure you're in degrees. I am now. And I'm going to go cos 280. What is the cosine of 280 degrees? 0.1736 has to go to 4 decimal places. Is that okay, Brianna? I want to find the sine of pi by 6. I'm telling you, if you did this, if you went sine of, first of all, you notice how there's more than one number here? What does that mean, physics humans, if there's more than one number? Brackets. If I do this, bracket 7 pi divided by 6, right now, that's wrong, because it did it in degrees. So before I do this, I need to go setup, down arrow, down arrow, down arrow, down arrow, down arrow, down arrow, radians. Who's in physics with me? You're going to have to get in the habit, physics, whenever we're doing trig, of going to degrees on the physics tests to radians here when I tell you to go radians. Sorry. Now, if I do it, there's the correct answer, -0.5. See if you can get that. The sine of 7 pi by 6 radians is negative 0.5. Try the cosine of 10 pi by 3. I should be able to do this one in my head. Let me think. 6 pi by 3. 3 pi. So it's down here. So it's going to be negative. And I'm out of practice. Reference angle is 1/3. 1 pi by 3. So it's the 1, 2, root 3 triangle. 1.71? No, I'm.
It's the same as the other one.
It's a half? Negative a half? Oh, it is. I should have got that. Find the sine of 90 radians. That one, I'm just going to go sine 90. And I get 0.8940. If I round off to 4 decimal places, right?
Sine, right?
Yep. You're in radians still.
No, I changed to degree.
There's no degree symbol there. Why are you changing to degrees? Just because it's a 90 and it looks like
I changed the setup to back to degree.
you shouldn't be, is what I'm. This is not degrees. There's no degree symbol there. You're still in radians.
Gotta watch out, that's where it's gonna itch you.
Next page. Yeah. Sorry. You're lost? Were you able to go from degrees to... Okay, let me come look. So, you ready? What we really want to talk about are what the graphs look like. This is where we're going to get tricky with it. On the next page, it says, investigating the graph of sine x in degrees and in radians. So this first chart here is in degrees. So can you put your calculators back to degrees, please? And a rule of thumb in this section, Chelsea, if you're getting weird answers, like bizarre, decimally yucky, first thing go check is make sure you're in the right mode. Are you in degrees or are you in radians? And make sure what the question wants you to be in. So we're all in degrees? What we're going to do is we're going to make a little table of values. Can you find the sine of 0 degrees, please? What's the sine of 0? Okay, so when x is 0, y is 0 if I'm graphing y equals sine x. Can you find the sine of 90 degrees, please? 1? Can you find the sine of 180 degrees, please? 0? I'm skipping I'm just doing every 90 degrees. I'm not going to do all of them. Can you find the sine of 270 degrees, please? Can you find the sine of 360 degrees, please? So if I were to graph this, if I'm graphing the equation y equals sine x, when x is 0, what's y? You with us where we are now, kiddo? Mm-hmm. I know, but I want you focused too. When x is 0, what's y? So this graph goes through 0, 0. What about when x is 90? What was y? So 90 goes through, and I guess 1 is way up here. They're using a scale. When x was 180, what was y? When x was 270, what was y? When x was 360, what was y? When x was 360, what was y? So we had constant function, linear function, quadratic parabola, weird cubic. What does this look like? Well, let's get out our graphing calculators. Let's go into the graph menu, menu 5, and let's type y equals, oh, first of all, delete any graphs you have there. And then let's type y equals sine x. Enter. Oh, but before we hit graph, let's match their graph paper with our view window. So looking at their graph paper, if I go shift view window, how far left does their graph go? Look at the graph paper. How far left does it go? No, right. And you know what? Let's go up by 90 degrees. Is that okay? Because that looks like where they put each number. Sorry. How far right does it go? Let me do the x max first. How far right? 540. And my scale is going to be 90 degrees. Okay. How low does their graph go? You know what? A little bit past -1. What's each square worth? How many squares make up 1? Each one's worth 0.2, I think. So I'm going to go negative 1.2 and positive 1.2. And what did you say each square was worth vertically? 0.2. Here is one of the most important graphs in the universe. This is the sine graph. Okay? Pardon me? It's a cycle. Yes? Yes! Absolutely, Jake. All waves, all sound waves, all light waves, all waves can be replicated with trig functions, in particular sine and cosine. But a whole bunch of other, anything that oscillates, you can represent it as a trig function. How many been on a swing set before? Okay, ready? Look, swing goes up, swing goes down, swing goes up, swing goes down, swing goes up. Trust me, you're graphing out a sine function or a cosine function. How many been on a Ferris wheel before? Ferris wheel goes up, Ferris wheel goes down. As time moves forward, this is how your height moves. Trust me, it's a trig function. Oh, the years, the length of daytime. Shorter in January, longer in June, shorter in December. It turns out the length of time of days, the amount of daylight we get, it carves out perfectly a lovely little trig function. They show up all over the place. The whole idea behind the synthesizer and digitizing sound is if we add trig functions on top of trig functions on top of trig, if we get a computer to do it for us, we can simulate, we can approximate any sound there is with a series of trig functions, and however accurate you want it to be is just what my compression level is. So, what do you notice the pattern is? Can you look up? First of all, it looks like every 90 degrees, I'm either at the top, or the middle, or the bottom, or the middle, or it goes top, middle, bottom, middle, top, middle, bottom, middle, top, middle, and every 90 degrees, every one of these, which is kind of nice. Nice way to think about it. So if I continued the pattern on this graph here, I think at 45 degrees, I'm at the 450 degrees, I'm at the top. Yes? And then where will I be on my next point? Where will I be on my next point? Rach, you with me? Where will I be on my next point? Middle. And if I go that way, top, middle, bottom, middle, top, middle. Here is the sine curve. Looks like that. What's the domain? Ah, what's the range? How high does this go? 1. How low does this go? Now, considering it could have been an ugly range, you can't ask for a much easier range to remember than between -1 and +1. I mean, that's pretty clean. Okay? We call this a periodic function. Why do we call this a periodic function? It repeats. In fact, the length of one period is from here, that's wrong, to here. Or the length of one period is from peak to peak. That's how long one period is. Or the length of one period is from valley to valley. This notion of, because Jake right away said it cycles, this notion of cycling, the fancy word, it's periodic, this notion of periodic functions, huge applications all over the place in electronics and computing and a lot of the stuff we do nowadays. So read along with me. It says, on the grid, copy the graph, we already did. This is a, here's your word you want to underline, periodic function. It continues to the left and right. So what did we say? The domain was all reals. What's the range? What did you say the range was? Between what? Touching? Yes. Okay. Put your pencils down and look up. I do not want to write between -1 and 1. That's way too much work. So you may recall you did learn how to show a range or a domain between two values. How did you do that? You always wrote the lowest value first. What's the lowest value of the range? Leave a space. You always wrote the biggest value last. To show everything's in between, we're going to put our variable in between those two. Range, is that X's or Y's? And then it was always less than. What that's saying, Taylor, is Y is bigger than, is above -1, while at the same time it's below +1. That's how you say in between. Dom, did you say it was touching? Oh. Or equal to, or equal to. That's the range. What's the y-intercept? What's the x-intercept? How many x-intercepts are there? An infinite number, because it keeps going. So all we can do is, instead of telling you what the x-intercepts are, we can just tell you how to find them. Where do they occur? Every what? Every 180 degrees. So the x-intercepts, here's how we write that. 180 degrees times n, comma, little n, where n is an integer. That looks terrifying, I know, but don't freak out. Write that down, I'll tell you what it means. It's saying if you want to find the first x-intercept, let n be 0. What's 180 times 0? There is an x-intercept at 0. You want to find the second one? Let n be 1. What's 180 times 1? There is a x-intercept at 180. Also, you can let n be 2. What's 180 times 2? That'll give you that one. Also, you can let n be 3. What's 180 times 3? Oh, but I said n is an integer, so it also can be negative. You could also go 180 times -1. That'll give you the -180. You can also go 180 times -2. That'll give you the -360. That's the shortest way to say, look, 180 degree, every 180 degrees going left and right, starting at 0. We're going to pause here. For now, the questions that you can do. Number 1. Number 2. Number 3. 4. 5. No, I haven't got to the graphs yet. But we're going to do number 2 together, because I'm going to show you clever ways that you can memorize a tiny bit and figure out the rest. So can you all look at number 2? Ready? Can you all look at, are you all on number 2? Yeah? Watch. Look up. In radians, what was once around the circle? Who remembers? 2 pi? So you ready? In radians, what was halfway around the circle? If you know that, you can now fill in the rest. I'll show you. What would 90 degrees be? Well, it's halfway to 180. Oh, it would be pi by 2, half a pi. Right? What would 45 degrees be? Half of 90. What?
Pi by 4.
Okay. How big? 45 degrees, pi by 4. 2 pi by 4s, which is also pi by 2. How many 45s is that one there? Ready? Here's 1. Here's 2. How many 45s is that one there? 3 of them. 3 pi by 4s. This angle right here is that. Oh, another way to think of pi, put a little comma in front of the 180. Because isn't 4 over 4 1? But it's 4 pi by 4s. Why is that so nice? Because if I go 1 more 45, that's 5 45s. That's 5 pi by 4s. Right? Go 1 more 45. This is 6 pi by 4s, except how would you write 6 over 4 in lowest terms? Oh, does that mean it's also 3 90s? Because 1 pi by 2 was a 90. 2 pi by 2 was 180. 3, oh, so this is also... So you ready? Watch with me. There's 145, 1 pi by 4. 2 pi by 4s, 3 pi by 4s, 4 pi by 4s, 5 pi by 4s, 6 pi by 4s. What's that one there? 7 pi by 4s is the same as, I think that's 315 degrees, but I know that's 7 pi by 4s. Okay? Now the second trick. How many degrees? 180. How many radians? How many degrees? What fraction of 180 is 60? 1/3. You know what? 60 degrees is pi by 3. What would 2 60s be? How many degrees? 120. Where is that? Right here. It's... Sorry, got a little far, Mr. Dueck. Right here, 60, let me get this right, Mr. Dueck. Yeah, right here. This is also 3 pi by 3s, because that's still pi. So now I'm worried that I got this in the wrong place.
I think it's the first one.
It's the first one.
Go after 9
Yeah.
degrees.
This is 2 pi by 3s. I normally don't put all these on one circle. 3 pi by 3s. Right there is 4 pi by 3s. Right here is 5 pi by 3s. And all the way around is 6 pi by 3s. And 6 over 3 is 2 pi. We can do the same trick with 30. 30 is what fraction of 180? pi over 6. So each one of these is 1/6 pi. 1/6, 2/6, 3/6, 4/6, 5/6, 5/6. See if you can fill in the rest. I'll let you try it.